Welcome to Physics in Your Life. This is a 36 lecture course on physics, its applications to everyday and some not so everyday events that occur in your life or affect you in your life. My name is Rich Wolfson. I'm a physics professor at Middlebury College when I'm not here at the teaching company. I'm also a physics researcher. I study the sun and its outer atmosphere, the eruptive outbursts that sometimes occur and affect us here on Earth. I also do a little bit of work in climate change, but my real love as a physicist is making science accessible to people who are not themselves scientists. And that's why I'm here with this course with the teaching company today. I remember a time in my early career at Middlebury College when I was invited to address a second grade class at a nearby elementary school. And the principal introduced me as a physicist and said that this was a kind of science that sounded, in this introduction, very obscure. It sounded like something very few people knew about. It sounded like something that had very little to do with everybody's lives, that went on in secret laboratories and so on. Physics is anything but that. Physics is something that has a major role in your everyday life. Physics governs almost everything you do. And the purpose of this course is to give you a sense of how that works. Take a look at the first visual here. It's a list of activities you might have done today. For example, have you driven a car? Have you flown in a plane? Have you used a computer, checked your email? Have you used a phone, a cell phone, or a regular old-fashioned phone? Have you listened to a CD or a tape? Have you watched a DVD or watched a videotape? Have you even done something as simple as walking or riding a bicycle? Simple things like that. Have you looked up and admired the blue sky or maybe looked at the clouds go by? Have you seen a rainbow? Have you kept warm despite it being cold out? Have you run your air conditioner and kept cool despite it being too hot out? All these things involve physics. And what they involve fundamentally is your interacting with the physical world, either the natural physical world that's been here since before we human beings came along, or increasingly the technological world that we've created around us. And that's really all physics is about. It's about the nature and the workings of physical reality, again, whether that's created physical reality that we've created technologically or natural physical reality that's already been there. Why should you know something about physics? Well, I think there are both philosophical and practical reasons for understanding the physics in the world around you. First of all, you get a better appreciation for the universe in which you live, I think, if you understand how it works. I've had people say, gee, if you understand so much about the universe, doesn't that take away the mystery and wonder of it? The opposite is true for me. I think it adds to the mystery and wonder of the universe. There's also a practical reason for knowing about the physics in your everyday life. It may make you, for example, a wiser user of technology. I think treating your computer as a total black box may get you by, but knowing a little bit about what goes on inside it may help you to use it more wisely, for example. Understanding how the anti-lock brakes work on your car, something I'll cover in a subsequent lecture, I think helps you to drive better and to drive safer. It may also make you a wiser steward of the natural world if you understand a little bit about the physical principles that govern the world. So my motivation for this course is to explore the application of physics in your everyday life, and that means, again, your everyday life that involves technology and your everyday life that involves natural phenomena. This is not a standard introductory physics course. It's completely out of sequence for such a course. It doesn't follow the prescribed set of physics principles. It's not a course that's going to lay out a lot of physical principles and then give you a few minor examples of them. Rather, it's going to focus more directly on the applications of those principles in your everyday life. On the other hand, it's not just a how things work explication. There are some wonderful books out there and websites and so on where you can look up how a refrigerator works or how a solar panel works or how your car steers or whatever else. And you'll learn about those things, but you won't learn as deeply as you will in this course about the underlying principles that govern them. So some of the lectures are going to be more technologically oriented. That'll be particularly true of the second lecture, as you'll see shortly. And others will lay out more of the principles. Sometimes we'll look at a technology or look at a natural phenomenon and we'll raise questions that we'll then answer with physics principles. Other times we'll look at physics principles and then use them to explore different applications. Today's lecture is an introductory one. I'm not going to get into any particular technologies or applications. My title, Realms of Physics, rather is designed to give you a sense of what the different areas of physics are that we're going to have to explore to understand everyday and natural and technological phenomena, and also to understand how those all fit together into a big, broad picture of what physics is about. Physics is divided into a number of realms. That's the reason for my title again, Realms of Physics. They're interrelated. They are not completely distinct and separated, so the separation into different realms is somewhat of a human artifact. It's somewhat of a historical artifact coming out of the context in which we developed our understanding of physics. And all of these realms have some bearing on our everyday lives. In the so-called everyday physics that I'm talking about here, the physics of walking, the physics of driving a car, the physics of much of the electronics revolution, but not all of it, for example. The physics behind that is what we call classical physics. And classical physics talks about our understanding of the physical world that was developed before about the year 1900, roughly. After 1900, two great big new ideas came into physics, which I will talk about more subsequently. And these ideas are the ideas of relativity and quantum physics, and they're properly topics for other courses. Classical physics was completely understood before the year 1900. And you might say, well, what kind of a course is it that's so old-fashioned that it's dealing with material that came up from over a century ago? Well, the answer is classical physics, although it's old-fashioned in the sense that we've known about it for centuries, literally about 100 years and more, and some of it for up to 300 years, is nevertheless very much alive and contemporary. Let me give you some examples. Classical physics completely explains how an airplane flies. So if one of the things you did today was fly on an airplane, that was completely governed by classical physics. When we land rovers on Mars and explore the surface of Mars, it's the laws of classical physics that tell us how to get the spacecraft to Mars, how to land it on Mars, how to roll it around Mars, and all the other things it does. When you step on the brakes in your car on an icy road, and nevertheless you stop safely because you've got anti-lock brakes, it's classical physics that dictates how the brakes work, how they stop the car, and so on. Classical physics is contemporary physics also. It's physics that governs many, many of the contemporary things we do and enjoy. And classical physics itself comes in a number of realms. And if you were to study an introductory physics course, these realms might be a little bit more distinct than they're going to be in this course. You would take a course in one of them and then a course in another one, and so on. First realm that one usually studies, although not the case in this course, is mechanics. That conjures up pictures of greasy old man or young man in wrenches and grubby blue jeans working under cars, but that's not what mechanics means. Mechanics means simply the study of motion, how things move, why things move, although we'll see subsequently that that may be a little bit of an oxymoron, that question. Mechanics we've understood for about 300 years. The name Isaac Newton is most singularly associated with mechanics, although Galileo and a number of others contributed substantially also. Classical mechanics typically involves, in an introductory physics course, things like throwing a tennis ball, throwing a baseball, firing a cannon, what have you. Motions of macroscopic size objects, cars rolling down hills, railroad tracks, railroad trains joining together, and so on. But classical physics, classical mechanics, goes a lot further than that. Down toward the atomic level, it doesn't quite get to the point of explaining individual atoms, but in many cases it explains the motion of individual molecules, for example, in a gas, and describes how gases work. That's almost completely describable by classical mechanics. At the larger scale, it covers things up to the size of stars, stars assembling themselves into galaxies, and galaxies assembling themselves into groups of galaxies. All those things fall under the rubric of classical mechanics. A second major area of classical physics is electromagnetism. This is a theory that grew out of a number of experiments begun as early as the ancient Greeks, who coined the word elektron for the substance amber, which had electrical properties, and continued on through the 17th and 18th and 19th centuries, particularly with experiments with primitive batteries, experiments with biophysics involving things like frogs' legs that you may have heard of, experiments involving the first ideas of the links between electricity and magnetism. And in fact, electromagnetism is a subject that joins these two previously thought to be separate fields of electricity and magnetism. By 1864, electromagnetism had come together as a single field. The equations, the laws, there are 4 of them that describe electromagnetism, were at that point completely understood. It was James Clerk Maxwell in the 1860s who put those 4 equations together and gave us our current complete classical understanding of electromagnetism. And it was Maxwell whose ideas also led to one of the most stunning discoveries in all of physics, the discovery that the nature of light is an electromagnetic nature. And today we know that light, radio, television, the microwaves that cook in this microwave oven, the radar that the police use to catch you speeding, the ultraviolet rays that give you a tan or worse, the X-rays that are used for medical diagnosis. All these things are fundamentally the same, and they're fundamentally electromagnetic waves. So electromagnetism is a major part of physics, and we'll deal with electromagnetism extensively in Module 3. There are obviously a great number of electromagnetic applications in our everyday lives. I mentioned that Maxwell in 1864 approximately discovered that light itself was an electromagnetic phenomenon. People had certainly known about light. Newton had made theories about what light was. Huygens had made theories about what light was back in the 17th century. But people really didn't understand the nature of light, and it was Maxwell who showed us that light is electromagnetic. Nevertheless, the behavior of light is such an important area of physics that it often is considered a field unto itself, although now we understand how it can be explained on the principles of electromagnetism. So another major realm of physics is optics, the study of light and its behavior. And classical optics, optics covered by Maxwell's theory of electromagnetism, tells us a lot of things. It tells us how to build instruments like microscopes. It tells us how to build telescopes. It tells us how to build eyeglasses. It tells us how my contact lenses work. It tells us how we reshape the cornea with lasers if you've had laser surgery to correct your vision. And there are many, many examples of optical phenomena in nature and in the universe around us. A compact disc, for example, which will be the topic of the second lecture, is read optically. Rainbows are optical phenomena. The behavior of the atmosphere, the reason there's a blue sky, is essentially an optical phenomenon. And furthermore, because light is essentially a wave, an electromagnetic wave, but nevertheless a wave, it shares with other kinds of waves, ocean waves, water waves, earthquake waves, you name it, lots of other kinds of waves, and particularly sound waves, many of its properties. And so many of the principles of optics that we'll talk about when we talk about optics will also apply to sound. And the last lecture in the first module of this course will deal with sound, and we'll apply some of these wave principles. I mentioned one of the things you might be doing or have done today was to keep warm when it was cold or keep cool when it was warm. And that's the province of thermodynamics, the study of heat and related phenomena. So these principles tell us how to keep warm in the cold or cold in the warm. They tell us why Earth, sitting surrounded by outer space, whose temperature is a frigid cold on average 3 degrees Celsius above absolute zero. That's pretty cold. How the Earth nevertheless manages to remain warm. On the other hand, the Earth is in the vicinity of a star, our sun, only 100 million miles away, and with a surface temperature of about 6,000 degrees Celsius. So how come the Earth isn't baking? Well, it's the principles of thermodynamics that determine the Earth's climate and also help us to understand the changes we human beings are causing in climate with our large-scale technological society. So thermodynamics is a really important topic. Another thing it tells us is why we can't build perfect engines, why your car can't extract every ounce of energy, it's not quite the right word, every joule of energy, I should say, from the gasoline you put into the tank at whatever price you're paying for it. Why, when we build a power plant, for example, we dump about 2/3 of the energy we extract from burning coal or fissioning uranium or burning gas or whatever we're doing. We dump 2/3 of that energy into the environment, typically into a river or other body of water, as waste heat. So these realms of physics are going to tell us a lot about everyday happenings in our lives. Now, classical physics does, as I said, an excellent job describing most everyday phenomena. But it isn't the ultimate end of physics, and that's why late in the 19th century there were a few little cracks in the structure of classical physics which grew around the year 1900 to glaring failures. Not failures of classical physics, again, to explain everyday phenomena. It did that very well. But failures to explain phenomena that were just beginning to be explored at that point. And I want to just describe briefly for you the different realms where classical physics fails, and then give you a sense of how the whole of physics fits together. I should say that the big ideas that go beyond classical physics are covered in my other teaching company course, Einstein's Relativity and the Quantum Revolution, Modern Physics for Non-Scientists. And I should say a little bit about the relationship of those two courses. Physicists would use a funny word for them. They would say those two are, in a sense, orthogonal. Now think about that word a second, ortho. It sort of means right angle. And it's an outgrowth of the idea that this direction and this direction are at right angles to each other and have nothing at all in common. And that idea, as used by physicists and mathematicians, has grown to mean structures, objects, concepts, whatever, that in fact go in a sense conceptually mutually perpendicular directions and therefore don't have a lot in common with each other. And that's the way with this course and my modern physics course. The modern physics course is about some big principles, mostly the principles, little about the applications, principles that were developed since the year 1900 that explain realms of the universe that we don't typically deal with in our everyday lives. This course is orthogonal in the sense that it covers realms of physics that deal with things that happen pretty much in our everyday lives. It's not quite the case that there's zero overlap. There are a few cases where concepts of modern physics will be important, and I'll mention those briefly in a minute. Let me mention the three areas, though, that I think take us outside the realm of classical physics, because it's good to understand those to see the big picture of where everything fits. And in all these cases, classical physics doesn't need to be thrown out. It can be considered an approximation that holds in some special circumstances. For example, in 1905, Albert Einstein posed his special theory of relativity. He didn't, by the way, name it that. He called his seminal paper on the subject On the Electrodynamics of Moving Bodies, because it was a work that grew out of some subtle conflicts that arose between classical Newtonian physics and the more modern electromagnetism. And for practical purposes, special relativity deals with situations where objects are moving relative to us or to our measuring instruments or to whatever, and I have to put that phrase relative in, at speeds approaching the speed of light. At speeds that are low compared to the speed of light, classical physics works just fine. So does special relativity. It has more complicated formulas, and they reduce in the limit of speeds becoming very small to the same equations of classical physics. So that's why I say classical physics is sort of a subset, a special case of relativity. We rarely deal in our everyday lives with objects moving at speeds approaching the speed of light. If our cars moved at near the speed of light, or equivalently, if the speed of light were, say, 100 miles an hour, then we would have grown up with an intuitive understanding of the universe as described by special relativity, and we wouldn't have needed Einstein to tell us about that. There are very few cases in our everyday lives where we have to worry about special relativity. I'll tell you one. We don't really have to worry about it, but if you are watching television or watching this course on an old-fashioned cathode ray tube type of screen as opposed to a modern flat panel LCD or plasma display, then the electrons that paint the picture on your TV screen are coming at you from the back of the TV tube at a speed of about 30% of the speed of light. So there's something that is important in your everyday life that is moving relative to you at a speed that's significant compared with the speed of light. And if the engineers who had designed your TV tube had used classical physics, your pictures would have been completely out of focus. Didn't happen because they did it right. Now, special relativity is special because it describes only situations in which observers who are measuring things about physical reality are moving uniformly. They aren't accelerating, they aren't going around in curves, and so on. Einstein developed by 1916 the general theory of relativity that subsumes the special theory and also turns out, for reasons I describe in my modern physics course, to become a theory of gravity. And Einstein's general relativity theory turns out to differ from Newton's theory of gravity only in very, very minor ways, unless gravity gets very strong, and we know only a few places in the universe where gravity is very strong. One is around black holes and neutron stars, which are collapsed stars, which have shrunk to the size of, a city or smaller, with all the mass of an object the size of the sun, and gravity becomes intensely strong, and Newtonian gravity fails us completely there. We also know that Newtonian gravity failed in the early universe when matter was extremely densely concentrated, and we know that it probably fails in overall descriptions of the large-scale universe, although whether that's true or not depends a little bit on the overall geometry of the universe. And again, I discussed that in my other course. But differences between general relativity and classical physics in the realm of our solar system are minuscule. However, there's one everyday application. You may not think it's everyday because you don't use it every day, but it's probably being used even today in your name, and within a decade it will be ubiquitous, and that's the global positioning system. It's such an important technology, and it's so wonderfully based in a variety of physics ideas that I'm going to dedicate a whole lecture to it in the final module of this course. But I will simply say that if the global positioning system timing did not take into account general relativistic effects of Earth's gravity as having to be described by general relativity, and also effects of special relativity due to the motions of the satellites, by the end of a day, the measurements of global positioning system instruments would be off by on the order of a mile. So there's one case where our technology is so exquisitely accurate that we can tell the difference between classical physics and this bigger realm. Finally, as we get down to the smallest scales possible, the size of atoms and smaller, we come into the realm of quantum physics. And so in some sense, quantum physics, since we're built up of atoms and molecules, the principles of quantum physics underlie our lives. But in the everyday applications of our lives, we rarely have to use quantum physics. There are, however, several places where quantum physics does become crucially important. One is the whole electronics revolution. A thorough understanding of the semiconductors at the basis of that revolution is an understanding that requires quantum physics. And I will give you both a classical and a quantum picture when I discuss semiconductors in Module 4. Another example is the laser, now so ubiquitous that whenever you buy groceries at a supermarket or buy something at a store, the barcode is scanned with a laser device, and those lasers intrinsically use principles of quantum physics. Now, ultimately, our goal as physicists is to describe all of physical reality with one single law. I've described for you three things. I've described general relativity, special relativity, and quantum physics. Well, only two things, because special relativity is subsumed under general relativity. But we have not figured out how to make those come together. So there is a search ongoing for a so-called theory of everything that would merge all these branches of physics in the way Maxwell and others merged electricity and magnetism and then optics into a single realm. We'd like to understand all of physics in terms of a single theory of everything, but we're not there yet. Will we be there in the next few decades? Some people think we will, and others are sure we won't. What we do know is that until we get there to a theory of everything, a theory that combines general relativity and quantum physics, we won't understand what happened in the very early universe, the very early microseconds of the universe, and we won't understand what's going on at the centers of black holes. Now, having said all that, let me just humble you a little bit. It sounds like I've built this big structure of physics, which is almost there to a theory of everything, and a minor part of that is going to be explaining our everyday lives, the physics of our everyday lives. But there's reason to be humble. Recent astronomical observations in the last couple decades particularly, combined with theories of particle physics, tell us that at most 5% of the stuff the universe is made of is the kind of matter we understand. The rest is some unknown dark matter and dark energy about which we know nothing. And that's a particularly humbling thought, that we know nothing about the rules that govern or the nature of 95% of the universe. So be humbled by that. Okay, let's get back to everyday physics. Let me tell you in the remainder of this lecture a little bit about this course and how I've organized it. It's divided into 6 modules. Each module has 6 lectures. Well, this introductory lecture is sort of outside, but then we'll begin Module 1 with the 5 remaining lectures in this 6-lecture set. Each of the first 5 modules corresponds to a particular area of physics or some related technology. And then the last is a kind of potpourri. It's ideas that went a little bit beyond what some of the individual module subjects would cover. It concludes ideas that draw from a number of different modules. For example, there's a lecture called Physics in Your Body, which will talk something about the mechanics of your body, something about the electrical effects of your body, electrical properties of your body, and a lot about medical imaging, which draw on some of the previous modules. So the last is a kind of hodgepodge, a potpourri. Each lecture is going to introduce a mix of applications and physics principles. Some will be more application-oriented, some will be more principle-oriented, but you'll get a mix of each. My goal, again, is not simply to say, how does this work, how does this work, how does this work, but to give you an understanding of the basic underlying principles that will get reinforced as we look at these different applications. My approach is entirely qualitative. There's no math. I believe you can understand physics and understand it deeply without using mathematics. I also believe that you can't understand it fully without using some mathematics, but this course is going to give you a good and deep conceptual understanding, and not doing mathematics is nothing at all to be ashamed of. I should say briefly that, well, there might be 1 or 2 cases where I show you a picture of an equation because it's so beautiful or I want you to know what it means, or in the case of Professor Williams' egg cooking formula, which will appear in my lecture on physics in the kitchen, for a little bit of humorous aside. I'll also say that at the end of each lecture, as with most teaching company lectures, there are some lists of suggested readings. In my case, this course is designed to stand on its own completely. You don't need to do any of the readings to understand more, but in many cases you'll find the readings satisfying and they'll go deeper. And the readings kind of fit into two categories. In one case, there are specific books or articles I've chosen that deal with particular technologies. How does the CD work? Medical imaging, technology and the automobile, and so on. But in other cases, there are some general books, and I've listed in particular two general physics texts. One is definitely a conceptual physics text, a text that looks at physics conceptually. The other is a calculus-based introductory physics course, and that's listed under the Going Deeper readings. And if you want to dig deeper, you can read books like that. In general, the books that are listed under Going Deeper, I have not stuck with the no math. So some of those books will be mathematics. The recommended readings, the simpler readings, are all also qualitative, basically math-free. And I've, as I said, ordered this differently than one would an introductory physics course, and I've chosen my order so that the first lecture, which is called the first module, which is called Sight and Sound, deals with the technology and then the physics principles behind hearing and seeing. Because what you're doing is watching and listening to this course on probably a DVD, possibly an old-fashioned video cassette. And in the remaining minutes of this lecture, let me just go through in outline the things we're going to see here. Okay, so here's an outline of, first of all, the major realms of physics that we looked at. Here's mechanics. I talked about mechanics. Here's electromagnetism. Here's thermodynamics. These are all some of the realms of physics we'll be covering. Here's optics. They together make up classical physics. I argued that classical physics is the dominant physics that will be covering what we deal with in this course. However, general relativity subsumes classical physics and includes things outside it. Quantum physics also subsumes classical physics and includes things that are outside classical physics, and general relativity and quantum physics do not fully overlap because we don't understand how to get them together. So there's a big conceptual picture of what all of physics looks like. What do the specific subjects we're going to deal with look like? Well, in Module 1, we've started with this introductory lecture on realms of physics. Lecture 2 is going to be highly technological. It's going to be on the amazing disk. Compact discs, DVDs, upcoming Blu-ray discs that you'll hear more and more about that will hold many times as much information as a DVD. We'll look at the amazing disk, and we'll use it to learn some of the physics of how these things work, but we'll also raise a number of questions that will help us to ask what physics principles we need to understand to go further. One thing we'll have to understand will be how waves work, so we'll look at the wonderful wave. We'll look at how we manage to see, form images, use digital cameras, and so on. We'll look at cases where seeing doesn't quite work, mirages, rainbows, natural phenomena like that, as well as one of the major technologies of today's society, the optical fiber. And finally, we'll apply what we know about waves to sound, music to your ears. The next module will be about motion, about the role of force in motion, about our misunderstandings of motion that have a lot to do with Aristotle over 2,000 years ago, about circular motion, which is very easy to understand, but also very easy to misunderstand. I'll have a lecture on flight, particularly how airplanes fly and other things. We'll talk about space flight. And a conservative streak, that sounds political, but it isn't. That's about the conservation laws for energy and momentum and what major roles they play in everyday physics. Module 3 is plug in, turn on. This is about electromagnetism. We'll understand how electricity is really at the heart of how matter behaves. We'll understand how we harness it, the role of magnetism, how we make electricity, how we use everything from a credit card to a power plant. You wouldn't think so, but they work on basically the same principle. And then we'll understand how electromagnetic waves arrive. Module 4 is more technological than physics. It takes us from the element silicon all the way through a complete computer. And we will build, actually, or figure out how to build a complex computer circuit. So there will be a logical building from the individual silicon atom to the computer. We'll see memory circuits along the way, logic circuits. We'll understand how semiconductors are made, and so forth. Module 5 is about keeping warm or keeping cool. How do we keep warm? What determines the temperature in this room, or the temperature of the earth, or the temperature of any other object, or the temperature of the water on the stove? We'll look at life in the greenhouse effect. We'll look at the tip of the iceberg about freezing and melting and thawing and boiling. We'll look at physics in the kitchen, because there's a lot of physics in cooking. Like a work of Shakespeare, that sounds like something from a literature course, but that, again, will be an example of physics, second law of thermodynamics, and we'll talk about energy in your life. And finally, we end with a module called Potpourri, your place on Earth, That's the one about the global positioning system. That's very technological. Dance and spin is about spinning motion, not only of dancers and ice skaters and people like that, but also of pulsars and protons in the magnetic resonance imaging systems that are used to imaging your body. The Light Fantastic introduces lasers, how they work. Nuclear Matters is about nuclear issues in our lives. Physics in Your Body, which draws heavily on some of the lectures just before it, looks again at the mechanics of your body and at medical imaging. And finally, the last lecture, Your Place in the Universe, gets more philosophical and looks at the big picture. There are several other teaching company courses, particularly Alex Filippenko's Astronomy and Neil deGrasse Tyson's Universe course, that go into that in much more detail. So that's where we're headed, and it looks like quite an adventure, and enjoy.